deeper about the concept of Ksp and then review it or reinforce it through a lecture demo. I wish we were doing it face-to-face, but given the circumstances, this is our best option. And I know you will do fine because I will be doing the activity with you just like we'll do it in class. Also, before I go into content, I would like to tell you that first and foremost, I wish you, your family, a safe and healthy distance learning experience. Already, elements, this is Mrs. Gupta, your AP Chemistry teacher. So I hope you all have watched the video that's already online on Ksp. And that video goes a little bit more numerical. So today I wanted to address a little bit more the concept of Ksp. Remember, we've been working on solubility equilibria for a while. We have done applied equilibrium to weak acids in form of Ka. We've applied equilibrium to weak bases in form of Kb. We've applied equilibrium to autoionization of water as Kw and many other cases. Today we are going to apply equilibrium to sparingly soluble salts. Sparingly soluble, sparingly means very, very little. Sparingly soluble salts are the ones that to our eye appear insoluble. So if you were to dump a bunch of salt into water, you'll say, oh yeah, it's not dissolving, because your eye cannot detect the very small amount that goes into solution. So the most common salt that you know, NaCl, actually is not sparingly soluble salt. The way you see NaCl is you take a tablespoon of salt, add it to a glass of water, it dissolves, right? So it's got pretty high solubility. Ksp is not applied to the salts with high solubility. This equilibrium expression is applied to salts that are sparingly soluble, like PbI2. PbI2, actually, if you recall, we call it a precipitate. So far, we were qualitatively judging our precipitate for their solubility. So we were saying soluble or insoluble based upon our solubility rules. Now we have another new criteria where for a precipitate, actually very small amount of it dissolves. And the amount that dissolves is to the power of 10 power negative 7, 10 power negative 8, even negative 14. But our sensitive equipment can measure that amount. So what happens in this sparingly soluble salt or precipitate? There is an equilibrium between the precipitate at the bottom and the small amount of ions that go in the solution, like the lead and iodide ions. And this equilibrium will be given in this case by molarity of Pb2 plus times molarity of I minus squared. Remember, because PbI2 will set an equilibrium with Pb2 plus and 2I minus. Because of this 2 coefficient, we will square the I minus concentration, and ideally it is divided by PbI2, but because PbI2 is a solid, we do not include it in equilibrium expression. So the Ksp expression for a sparingly soluble salt looks like this. Let's take example of another precipitate like PbCO3, right? This is again a precipitate, so you might be confused here. So we can apply Ksp equilibrium either to a precipitate or to a salt that dissolves in very, very small amounts. So it looks like it's just sitting in the solution, right? So most of the example I have here are precipitates, but this applies as well to a sparingly soluble salt that has made a saturated solution. It has dissolved as much as can go into solution at that point. And then between the solid precipitate and its ion, an equilibrium is established. So here between PbCO3 and Pb2 plus and CO3 2 minus, an equilibrium is established, which is really showing how this PbCO3 dissociates into ions. So Pb2 plus, CO3 2 minus, and then when we write Ksp expression, it's molarity of Pb2 plus times molarity of CO3 2 minus. And there is another way to create a precipitate, right? How do you create precipitate? You mix solutions. For example, if I wanted to create a precipitate of PbCl2, I know that PbCl2 is a precipitate. I can't really dissolve it, right? So how you make PbCl2 is you take aqueous solution of lead 2 nitrate and you take aqueous solution of HCl, mix them together, and you have some spectator ion HNO3 and PbCl2 as precipitate. So if you were to look at its particulate level drawing here, what you see is you mix PbNO3 twice, mole ratios are right here, HCl, everything is separated. I didn't have enough space here, so they kind of look scrunched together. But when you draw them, be sure to draw them separated because they are aqueous. Now as the precipitate forms, you draw Pb2 plus ClCl here, Pb2 plus ClCl here, and HNO3 separated. These are not together, they are separated from each other because these are spectator ions. The common question that students ask is, can they just write PbCl2 here as well instead of writing Pb2 plus 2Cl minus? Sure, you can, as long as your mole ratios are correct. And now the equilibrium, a part of it, so once the precipitate forms, a very, very small fraction of this precipitate will go in the solution to break into Pb2 plus and 2Cl minus ions. And the equilibrium between PbCl2 and Pb2 plus and 2Cl minus ions can be given by Ksp. So what we know from here, if we have a sparingly soluble salt or a precipitate, we can write a Ksp expression because there is an equilibrium established between the very, 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 very small amount of precipitate or sparingly soluble salt in a saturated solution that will go into ions, and this is given by Ksp. So just like Ka and Kb, the larger the value of Ksp, the more soluble is the sparingly soluble salt, just like our other K correlations. Alrighty, so from here I'm going to take you to the activity, and if there are things that you don't get about Ksp, please don't worry, because we will have a YouTube live session tomorrow where I will answer all your questions on this. Okay, so please document your questions or put them on Facebook group. I am connected with you through Facebook group. I will address all your questions. All right, now moving on to Ksp activity. This was given to you in a packet, and if you don't have it, you can use this video to write it on a separate sheet of paper, okay, or take a screenshot of it as I go up. Okay, this is an activity from Dartmouth's Gen Chem, and this is to show you that you are actually learning stuff here at first year college chemistry level, because you will be able to do it. So here they are talking about, so this activity, the purpose of this is to run a lecture demo side by side, so you can kind of see what the solutions look like and what the precipitate look like, and then answer the questions. And I even challenge you to think about what's happening at particulate level for every activity. So here we're going to be looking at two insoluble salts. One is lead 2 carbonate or lead carbonate, which is white, and a yellow precipitate of lead iodide, PbI2. When we put or create these precipitates and there is an aqueous solution, then a very, very, very small amount of this goes into ions. And how much of PbCO3 will go into ions is given by Ksp value. So minus x, x and x. So Ksp is equal to x squared. So if you square root it, roughly 10 to the power 7 molarity worth of Pb2 plus are present and 10 power negative 7 molarity worth of CO3 2 minus are present. So you see it's very, very, very small. So now let's engage in a lecture demo activity so you can actually see the solutions. So first they ask you to combine, and I will work on this with you. So I suggest that you listen to me for a bit more and then you pause it. So you do your work before you see my answer. That will be the best way to learn. So continue listening till I say pause it here. Okay. So now we're going to combine 5 mils of 0.10 molarity sodium carbonate. And I have that here. This is stock of 0.1 molarity sodium carbonate. And from this stock, I have poured out, you can see exactly here, but in this grad cylinder I've taken 5 mils of sodium carbonate, and now I'm going to pour it, and I'm going to remove this so you can see it better. So this is sodium carbonate, 5 mils, 0.1 molar, and I poured it in a test tube. This is 0.5 mils of sodium carbonate. At this point, it might be beneficial for you to draw a particulate level of this. I'm going to pause for a minute. The activity doesn't ask for it, but I want you to do it. On a side, create a small beaker or test tube or a field of view where you create 2 formula units of sodium carbonate aqueous solution. What will it look like? Note there is no precipitate, it's absolutely clear. Pause it here, don't peek at my work, do your own. And when you are done, then you can look at this work. Because we are making 2 formula units, there are 2 CO3, 2 minuses and 4 Na pluses. Everything is dissociated. Okay. Now we are asked to add 5 mils of 0.1 molar lead nitrate. This was 0.1 molar lead nitrate stock, and from here I took 5 mils of 0.1 molar lead nitrate. Take a minute and draw 2 formula units of it. Because they are in 2 to 1 mole ratio, you draw them as such. Okay. Now this part is confusing, so I'm not asking you to pause yet. I want to model for you. So here they say, will precipitation occur is the first thing. We are predicting if we mix these two, will precipitation occur. I suggest you write the overall equation before that. They don't, because this is a college class and they know that they have mastered writing equations, but I suggest that you start here. So write the equation that will happen: sodium carbonate aqueous plus lead 2 nitrate aqueous. You know it's a double replacement reaction, single side arrow. Sodium goes with nitrate, so 2NaNO3 aqueous and PbCO3 precipitate. So now they want you to calculate ion concentration before precipitation, before they mix with each other, right? How would you get that? You will get moles of moles of CO3 by multiplying molarity and volume together. So you will get molarity of Na2CO3, moles of Na2CO3, which will be the same as moles of CO3 2 minus. And then to get molarity of CO3 2 minus, you will divide those moles by total volume of Na2CO3 and PbNO3 twice, because PbNO3 twice is adding volume but is not adding carbonate ions. So before precipitation, what is the molarity of carbonate? And I'm going to show you that. I'm going to save these two solutions in a side beaker. So I get 0.05 molarity of carbonate, and I'll show you my work here on the side. So molarity of sodium carbonate will be, oh, you can see it, just like the class. So molarity of sodium carbonate is 0.10 mil, and we used 0.10 molarity, and we use 5 mils, or 0.005 liters of it. So moles of sodium carbonate, and because in one sodium carbonate there's one carbonate, you have 1 mole is the same as mole of carbonate, which is molarity 0.10 times 0.005. So that is 5 times 10 power negative 4 moles. So molarity of carbonate will be this divided by total volume, which is 5 and 5 10 mils, or 0.01 liters. Hence it is 0.05 or 5 times 10 power negative 2 molarity. Now please pause it and calculate lead 2 plus molarity. Show me the work just like I have done. You might want to pause it and restart the video when you're done showing the work for calculating Pb2 plus. Okay, welcome back. Hopefully you calculated Pb2 plus using the same method as we did for Na2CO3 and CO3 2 minus, and hopefully you got the molarity of Pb2 plus to be 0.05 molarity. The next thing that they ask you to do is to calculate Q. Just to refresh your memory, Q is different from Ksp in that the ion product is not at equilibrium yet. So Q, which is reaction quotient, is not equal to Ksp because we haven't achieved equilibrium yet. So to calculate Q, we use the same expression, molarity of Pb2 plus times molarity of CO3 2 minus. And how did we get that? Remember, we got it from the equilibrium expression of solid lead carbonate with its ions in dissolved state. Remember, this will be very, very small amount, but it is measurable. So based upon this equation, we calculated Q. And now please pause the video and I want you to calculate the Q. Welcome back. After pausing, hopefully your Q value is 0.025, and note that we don't have units here because we don't write units for Q or Ksp. Now to predict whether a precipitate will form, we compare Q with Ksp. So how much is Q? We calculated it to be 0.025. That's how much is the product of ions we have. How much is our Ksp? Ksp given for lead carbonate is 3.3 times 10 power negative 14. So way higher. So because Q is greater than Ksp, we can say that the precipitate will occur. Now let's check our prediction by mixing the two solutions and seeing if a precipitate will occur. And here I have the 2 test tubes in my hand and I want to mix these solutions together. Let me remove it. Whoa! When I mix these 2 solutions together, you see a white precipitate is formed. Right? So our prediction is correct. At this point, I encourage you to make a particulate level drawing, even the activity doesn't ask for it. Please pause and draw particulate level drawing. Welcome back. Your particulate level drawing at this point should look like this. We started with 2 formula units of each, right? So now we will have PbCO3 at the bottom. So you can either write Pb2 plus and then 2 CO3s next to it. Or just PbCO3. And in the solution, you will still have 4 sodiums, sodium ions, and 4 nitrate ions. These are spectators. They were present in the solution before the reaction. They are present in the solution after the reaction and completely unchanged. Okay, so that is what is being represented at this point. Now I have to move because the light has gone off. Let me see if this is actually better. Probably this might be better, so I'm going to leave the light turned off. Okay, now they ask you to calculate Ksp after precipitation. Okay, ion concentrations after precipitation. Because you had, so this part gets confusing. What do they mean by ion concentrations after precipitation? You see, you took carbonate and lead ion in 1:1 ratio, and our reaction tells us that they react in a 1:1 ratio, right? So you will have no ions left after precipitation, so 0 and 0. All of the lead and carbonate would have precipitated, and part of it will go back and set the Ksp equilibrium. So the ion concentration after precipitation will be determined by lead and carbonate ion from Ksp expression. So you square root 3.3 times 10 power negative 14 and you'll get lead ion concentration and carbonate, right? So immediately after precipitation you will have no lead, no carbonate, because that has gone into precipitate. But in a while, once the equilibrium is established, then square root of this worth of lead and carbonate will be formed. And then when they ask you for equilibrium concentrations, you will write that value. Let me see if I have that work done. I have so much work done. I don't know where it is. I can always square root it and figure out the value. Okay, where's my calculator when you need it? Here we go. So equilibrium, oh, I think I have it. Yep, found it. So equilibrium concentration of lead ion, remember this is determined by Ksp, and carbonate is 1.82 times 10 power negative 7 molarity. Now I encourage you to do the second part of this activity on your own. So the second part is part 2, which is, now first we explored PbCO3 expression, right? Now we're going to be mixing Ki and lead nitrate together to create an equilibrium for PbI2. I strongly urge you to pause the video at this point and please do this on your own. Once you are done finishing this page all the way till solubility equilibrium reaction, I ask you to start the video again, check your answer, go back, check your answer, and note any questions you have for me to be asked tomorrow. Okay? Okay, so the question asks, we have mixed what is the molarity of iodide ions before we mix after mixing the two solution. So you take molarity times volume to calculate moles of Ki. That's the same amount of moles as I minus divided by total volume, which is 15 mils. 10 and 5, 15 mils, and you'll get 0.067 molarity here. To get the molarity of lead ions, again first get the moles of lead nitrate by multiplying molarity with volume and dividing by total volume of 15 mils, and you get molarity of lead ions as 0.033. The Q expression will come from K expression, which is PbI2 solid creates an equilibrium between lead ion and 2 iodide ions. So how this expression is different from previous one is there are 2 iodides formed per PbI2. So when minus X of this dissolves, X of this and 2X of this is formed, right? That's how this is different. So you take 0.033 molarity of this, 0.067 of this, and square it. Note that square. I've written it in green so that you pay attention, because we know how much of iodide we are mixing, but we need to square it because there's a coefficient of 2. And that gives us the Q of 1.48 times 10 power negative 4. Now what do we predict? Will a precipitate form? Yes. So let's mix again the solution of Ki. Let me go get Ki from over there. So I have 5 mils of this is 5 mils of Ki. 10 mils. Okay, this is 10 mils of Ki and 5 mils of lead nitrate. This is 10 mils of Ki and 5 mils of lead nitrate. Okay, I'm going to mix the two. Whoa, and you see a bright yellow lead iodide precipitate forms. Okay, so your prediction was right here. And now let's write solubility expression here. So after precipitation, no ions are left because they were mixed in 1 to 2 mole ratio, and they completely reacted with each other and formed a precipitate. Now we write Ksp expression, which is Pb molarity I minus squared at equilibrium. So how do we get these values? We know when in PbI2 solid forms Pb2 plus 2 I minus. So when X of it dissolves, X and 2X of this is formed, right? So you put X and then you put 2X of this and then you square it. And this is what confuses lots of students, right? So yes, it is 2X squared. Okay, so generally, so when this is making this, right? So now in this case, it will be 4 x cubed is equal to 1.4 times 10 power negative 8, and when you do that you get the x value as 1.52 times 10 power negative 3, and iodide will be 2x times that. So you multiply this by 2 to get iodide. So that is part 2 of the lecture demo activity. Pause the video here if you need more time to interact with it. Go back, move forward, and make sense of it before we move on to the next part. Now, in the third part, elements, part 3, I suggest that we only go till solubility. This one gets trickier, so let's not do the solubility equilibrium after precipitation. Let's just do will a precipitation occur and only till here. Okay, now in the third activity we are looking to see which precipitate will form when you add lead to a mixture of iodide and carbonate. So just to clarify, what they are asking here is you have a solution, and in this solution you have two things. You have iodide ions and you have carbonate ions, and what you're adding from outside is lead ions, right? Remember, you can't just add ions, so there must be a spectator ion with each of those, and lead with iodide will form PbI2 and lead with carbonate will form PbCO3. What they are asking is which one will precipitate first. Well, the one where the Q exceeds Ksp first will precipitate first. So what you need to do is using moles, total volume, you need to calculate moles using molarity and the volumes, and then figure out how much of lead and carbonate, or how much of lead you need to precipitate out lead iodide and how much of lead you need to precipitate out lead carbonate. The one which requires less to precipitate out will precipitate first. And the work for this, you may want to pause it here again and do the work, and then I will show you the answers. The answers are here. So first, how we proceed is we get carbonate's molarity by multiplying volume and molarity of sodium carbonate to get moles of sodium carbonate, and because in 1 mole of sodium carbonate we have 1 mole of carbonate, that will be moles of carbonate, and then we divide it by total volume, which will be 10 plus 5 plus 5, or 20 mils in this case. So you get 0.025 molarity of carbonate. Similarly, to get molarity of lead ion, we get moles of lead nitrate by multiplying volume and molarity and divided by again 20 mils, that will be molarity of lead nitrate, which will be same as molarity of lead ion. And using similar process, we get molarity of iodide by multiplying volume with molarity of Ki dividing by total volume, that will be the molarity of iodide. Now for the least soluble salt, how do we calculate Q? So solubility, remember, is given by Ksp. So if you compare the Ksp of two of these, which one is a lower value? Lead carbonate, right? Because its Ksp is lesser. So the Q expression for the least soluble salt will be the expression for lead carbonate, which will be PbCO3 solid equilibrium sign Pb ions aqueous plus CO3 2 minus aqueous, right? And from that we write this Q expression, molarity of Pb times molarity of carbonate. So the Q value for PbCO3 comes out to be 6.25 times 10 power negative 4. And given that our Q is greater than the Ksp given for PbCO3, we predict a precipitate. And yes, a precipitate will form. Now the Q expression for the more soluble salt for PbI2 will be like this. Now in this case, elements, note that we are not doing 2I. Why? Because iodide, if you notice here, is coming from Ki. In 1 mole of Ki, we have 1 mole of I minus. 1 mole of Ki, we have 1 mole of I minus, right? In PbI2, from 1 mole of PbI2, we had 2 moles of I minus. But this is different here. Ki is making I minus. So we multiply molarity and volume. That will be moles of Ki. That will be same as moles of I minus. Then you divide it by total volume. That will be molarity of I minus. So we write that, but we still square it. So we don't have a 2 in front of I, but we still square it, because when you write the Ksp expression for PbI2, it's Pb2 plus 2I minus. So there is still a 2 here, which shows up here and here. But there is no 2 here, because in Ki there is only 1 I minus. Okay, and we predict that a precipitate forms, which it does. So I'm going to stop here, and the next part gets a little bit more challenging and beyond our scope. So we're not going to do it. We're just going to do it here. I suggest that you do this activity, do the calculations couple of times on your own to really understand it. And from here, try and do some Ksp problems from your yellow packet. And tomorrow, I will have a YouTube live session for answering your questions on Ksp activity or Ksp problems. And Ksp problems in here in the packet, in the yellow packet, are on page 12 and 13. Page 12 and page 13. Okay, so please do them, and we will connect tomorrow via YouTube live session. Okay, thank you for listening, elements.